So now for the second half of this morning session, we had the pleasure to have a talk on quantum clouds by Kaiser, Norbert, Mauser. Okay, so your height.
Okay, thank you, Francois, and thank you, Pierre-Louis, again for hosting us in the honor of Claude. So, part of my talk is already the affiliations. So you see the Wolfgang Pauli Institute, which is what Claude always calls a laboratory without walls. So now this conference here is co-organized from Vienna. So there is no agent comptable, no complication to co-fund the event, to co-organize. So Pauli Institute is a non-local object like Wolfgang Pauli as a quantum physicist would like. I'm also affiliated at the University of Vienna, working with people in physics, as you will see also in my talk. And since 2004, we also carry a Unité Mixte Nationale de CNRS, which is now called International Research Laboratory. So there's also a CNRS institute outside France. So if you want to work for a longer period in Vienna, you can go on délégation, détachement. It's relatively easy, and Vienna for French is like a clean, nice suburb of Paris. So we celebrate the 85th anniversary of Claude. Let's wind back the clock for his 80th birthday. So this is a Zoom picture of the 4th of April. So Claude is 4/4/40, his birthday, when Edris Titi, who could not come today, he's a very good dear friend of the community, he came up with the idea of making a Zoom birthday meeting. Everybody with 2 glasses of champagne. So some people, I and Inma, we were in my house, so some people could make the glasses sound. So well, I mean, 5 years ago, an event like this would have been impossible. Remember how strange it was. There was a pandemic, but then there were measures which were very strict in France. You couldn't leave your home for more than 1 hour. It was very strange. So it was very, I have to say, it's quite, one should work it out. How could we let us deal like this? Why did we accept all this? We knew it at the time. We know it for sure now. Partly completely crazy rules, okay? So anyhow, 5 years ago, for the 80th birthday of Claude, we could only do it by Zoom, and I hope for the 90th birthday of Claude, we will reconvene again in person. There will be no pandemic. The Russians will not invade France. So this was 5 years ago. Now, let's wind the clock back to April 2004, so 21 years, when Pierre-Louis was giving the opening talk of the 2nd annual meeting of the Hike Network. I will comment on that, which is also, so this was in the École Normale. You see, it was again organized from Vienna by me with Maria Esteban, Jean Dolbeau, and François Bouchu, and these were all, and Benoît Pertam. I will comment on that. So there we had freedom to move. This was 21 years ago. The world was much easier, much less rules. I could take my car, just enter École Normale, park my car in the Cours Pasteur. Life was much easier, and I claim better at that time. So this Hike Network was a huge European network in the 5th framework program. We had a relatively low budget. We had 3 million euro. One ERC grant, one ERC advanced grant is about 2 million euro today. And everybody who was participating in this open structure, this was really an open society project, knows that the scientific impact, the impact on careers of people, was larger by a factor of 100 than any ERC grant. So unfortunately, the European Commission stopped this kind of projects, and now most of the money goes into these ERC grants that have a certain value, but from the taxpayers' money leverage, this was one of the most efficient networks. So it was, in the end, we had 350 participating scientists, 40% of them in France. And the scientific idea was to put hyperbolic conservation laws and kinetic equations in one roof. And this was an idea that was partly discussed, you know, the apartment of Claude in Avenue Trudaine, we call it Château Trudaine, which is my Paris headquarters for, so I met Claude in, one has to always to mention that. Pardon?
I always thought it was wine.
No, it's Château Trudaine. So I met Claude in 1992, which was a very good year. because I could finish a very important paper in my thesis. It was the year where I personally met Pierre-Louis for the first time in Monte Cardini Terme, together with Benoit. And it was the year also where I met Claude at some very interesting meeting. This was a German-Jewish meeting for some reconciliation in '92. And it was, they had the German Taktgefühl to put it in Gosen, outside of Berlin, in a former summer camp of the Stasi, of the secret police. So I went there by car. So I was staying in West Berlin, and Claude was there, and we immediately sympathized. So I was one of the few French speaking, and he said, "Tu as une bagnole, tu peux me sortir d'ici." So I had a car, so I took Claude, and he stayed overnight in my place, because he was fed up of this being this concrete building where the Stasi officers had their summer camps. So this was in '92 when I met Claude. And ever since, when I'm in Paris, I stay in Claude's place. And the only price I will talk about is generosity. I wanted to give him money. He said, "No, no, no. Tu m'organises un pot." So every time I'm at Claude's place, I organize a dinner, I cook, and I invite the people. And that's all Claude don't ask for, but gets in return with generosity. So this was a scientific idea. So HIKE is an acronym that actually Gerhard Rhein was the head of the team in Vienna was inventing. And we knew once we have the acronym, the proposal will go through. So you have to be a nominalist. So once you have the good name, the good acronym, it's really helpful in the psychology of referees. So this was an idea that actually in the planning phase, so I was lucky to be at Courant for a year as a postdoc, when everybody was there, Louis Nirenberg, Kathleen Morawetz, Peter Lax, Andy Maider. So, and I had discussions, especially with Peter Lax, who is also a Hungarian Jew working in the United States now, with strong connections to Vienna. So he went to Vienna to Pauli several times. And so with Peter, he says, well, it's natural. You should put that together. The separation of hyperbolic conservation laws and kinetic equations doesn't make sense. So if you do a project, this would be very good for science. And there were other like Luis Caffarelli and the Fermos, the father. So this was, the idea was evolving over years in the planning phase. So it was at Courant. Actually at Courant, there was a conference in the year 2000. Let's wind back once more. I organized a conference with Mary Pugh, Nonlinear Analysis 2000 Era to the Future, which was one of the most successful things I did, because we decided, the organizing committee, we only invite people up to the mid-30s and people above 60. All the power brokers in the middle, we don't invite. So there were the Courant people like Maida, Lex, and all the others. They enjoyed a lot the conference, and there were the young people and the 200 participants. We had 600 demands, so we had to take 1 out of 3 to go to a conference. And these were really all the people that are Felix Otto, and everybody was there in nonlinear analysis, and these are all of them are stayed in research and are full professors now. And at that conference, it's my pleasure to see Hatem Sag again, because I remember he was in his wheelchair, and I pushed him on stage in the Angelica Auditoire, so it's really nice that Hatem, who was there at the conference. So at this conference, there was a long talk between Claude Bardos, Peter Lex, and myself, and then they asked me to do the work to go for this network, which was really an open laboratory. And thanks a lot to Benoit Bertam. He was the partner, my scientist in charge. And it was really, really the axis, Vienna, Paris, Vienna, France, that made Europe turn for these 3 years. And we had 127 young researchers being mobile. We paid grants and not working contracts. And I was founding Pauli Institute, designed to run this big project. I knew if I would do that on a university administration, it would be so complicated, it would not be able to transmit the scientific vision into something that works. So we founded a private institution, an ISPL, a non-profit association, in order to run this. So this is a laboratory without walls, exactly in the spirit that Claude is always. And also thanks to Jean Dolbeau and Marie Esteban, so the Ceremade at the time was also one of the headquarters of this project. Now let's go to equations. So François talked about kinetic Claude. I talk about quantum Claude, because Claude is most known for his work in classical fluid dynamics, but he also did some significant work in quantum theory. So first I want to combine those to quantum kinetic. My talk is not meant as a lecture. You will not understand everything, but I want to give you a glimpse, those who are insiders, will be bored because they know all this. For the others, I just want to give you the ideas. So quantum mechanics, the equation, the basic equation, the Schrödinger equation. Here you have some potential. If it's given, it's linear. If it's depending on psi, it's not linear. I will comment on that later. So this is a complex valued function. But you can do a phase-based picture of quantum mechanics. You know, there's also kinetic formulation of PDE, something that Pierre-Louis was involved with others. So this is in a similar spirit. So you set up a quadratic quantity, which is called the density matrix. You evaluate it at center of mass and relative coordinates. You bring in a scale. The epsilon here is the same as here, so that's a choice. There could be two different scales. So you transform the wave function in physical space, xt, into an object in phase space, so you have a kinetic variable here. And so this is the so-called Wigner function that was invented by Eugene Wigner a long time ago, 100 years ago. And you do some Fourier transform with respect to the relative variable, and then you end up with a phase space object. And then, of course, the Schrödinger equation, that's a little computation all my PhD students have to do. You convert the Schrödinger equation into the Wigner equation, and since you have a Fourier transform, you will get a pseudo-differential operator with the symbol of the difference of this potential. And if you look at this, this would converge to the gradient of the potential when epsilon goes to 0. So formally, you see immediately Blasov equation hidden behind. So that's the quantum Blasov equation, has the free transport operator. But the price to pay is this function here is real, but it changes sign, it oscillates. That's clear. By quantum mechanics, by the Heisenberg principle, you cannot simultaneously measure position and velocity or momentum. So there is a price to pay. It has all the good properties of a distribution function. Besides, it can have negative signs. Okay? And there is something there is an expression, les mesures de Wigner, the Wigner measures. This was coined by Pierre-Louis and Thierry Paul. In the limit, when epsilon goes to 0, it converges towards a non-negative Rado measure. That is the Wigner measure. One has to quote Patrick Gerard, who introduced the semi-classical measures, and this is also related to the age measures of Luc Tartat in some sense. So this is something for the aficionados. This is a very nice tool to measure the effect of compactness. Now, these Wigner transforms are used in physics. People in quantum optics, they use them. For us, it's a tool to do the semi-classical limit from quantum to classical. You can do higher wave number limits and general homogeneity limits. So that's a tool. And just to mention one last detail here. So if you make Schrödinger coupled to Poisson, so the density is the square of the modulus of the wave function. Here, the density is the zero moment in velocity of this phase space function. So you have Schrödinger coupled to Poisson, and it converges to Blasov coupled to Poisson. This was an outstanding problem that many people tried, and within a couple of weeks, Leon Spoll and Markovich Mauser, we found a trick that was technically very important. So Thierry came up with the approach with coherent states. I found the paper Hushimi written during World War II. You smooth the Wigner function with Gaussians, and so you can converge towards a delta, and you recover the classical equation. Okay, so that's just a glimpse. So this was the tool. So there was this Wigner function, and this is a very good tool to pass from quantum to classical. So for scaling limits where you live on the scale of the Planck constant. So at the end of my thesis, of course, at the time, everybody was applying for postdoc positions, so there was a fantastic grant scheme in Austria, this Schrödinger stipendium, and I had given a talk on Wigner functions at Courant in 93 or so, and Peter Lex was there. He did not fall asleep, so people really liked it. Huang Xiaoyao was there, and then Dave McLaughlin. Is Dave here? He should come. So Dave McLaughlin was the director of Courant at that time. So Dave then told me, well, you can apply to become visiting member. You get the invitation letter of Courant. So he wrote me himself a letter on high frequency limits. So I was thinking, what should be the project? Okay, I know that people at Courant would accept me. So I was sitting with Claude in Chateau Truden. And then Claude said, well, now that you have this fantastic tool, and there were three groups. There was George Papadikolaou in Stanford, who used this kind of Wigner transforms with, for example, Lenya Rizhik. There was Pierre-Louis, there was the French, Patrick Gerard, Pierre-Louis, the French, and there was Peter Markovich and myself and some others in Berlin at that time. that really knew how to handle this tool. So Claude said, well, go for something hard. Don't do easy stuff. You're a postdoc then. And he told me, there is something morally. Claude is always on the quest of going from reversible to irreversible. That's one of the leitmotif of Claude. So stochasticism, randomness implies. So temperature, non-zero temperature in physics, you always model with some stochastic. The definition of temperature is highly non-trivial, but you can roughly say there is some link between stochasticity, temperature, and irreversibility. So the goal was to derive the linear Boltzmann equation from the Schrödinger equation with stochastic potential. So this potential, this was in my equation here. This potential, you make it a stochastic potential, you put in a scaling parameter, it's some sort of quantum Lorentz gas, so there is a lot of work already done on that on the classical level. Herbert Spohn was pointing out some approach. So this was not done, but it was clear the new tool of Wigner transforms could be the tool to do it. And when I was at Courant, Huang-Tse Yao, after my talk, asked me to his office, and he was squeezing out of me for 2 afternoons. And then he said, now I learned it, and then I could leave the room. Everything I knew about Wigner transforms, especially there was the paper of Pierre-Louis and Thierry Paul only in French, Sur les mesures de Wigner. And there was no English translation. So Huang-Tse Yao, I explained him everything that is in the paper and everything I knew and what was unpublished about Wigner transforms. And then Claude said, well, if you have a contact with Huang-Tse Yao, this is one of the strongest stochastic analysts there. So if you do a project, we can do it together. I have some ideas. So I put it in my proposal, but then I made a mistake. So Peter Marquis told me, are you crazy? You do only one application as a postdoc. People write 50 applications. So I wrote a second one for a Marie Curie grant to go to Nice with Frédéric Poupeau. And of course, I got both. And then I could not postpone the European grant. It was impossible, but the Austrians allowed me to postpone the beginning of the grant for 2 years. So I went to Nice, worked with Frédéric. This was very fruitful and some other things. But then when I came to Courant, the day I arrived, 2 things happened. The first thing was Dave McLaughlin invited me for a coffee and told me, look, Norbert, our high frequency limit, this pneumatic liquid crystal stuff, I don't work on that anymore. I'm working on neuroscience now. You can join us if you want, but what you wrote in your project, I'm not in it. Find somebody else. So this was the one news on that day. The second news on the floor, I meet László Erdős with paper preprints. In the good old days, you made a preprint that you sent by mail with a handwritten letter to your friends. Look, I have done this work. I meet László on the floor with a preprint of his work with Huang-Tse, exactly doing what I had sketched in my proposal. So let me make it clear. The technique is terrible. What you have to do there, I mean, you really need the finest analyst in combination to do it. But the idea how to employ the Wigner transform, this was what I had worked out with Claude. So our first paper, we started too late, was written by somebody else. So then what we did with Claude was derivation of effective nonlinear mean field equations. So you put a 1 over n in front of the interaction. That's something also you do in classical things. So you call it a weak coupling limit. And you want to get rid of the n particle problem and do a nonlinear 1 particle problem. So there is a whole zoo of nonlinear Schrödinger equations. So if there would be a potential V given, this would be the linear case. Now in the nonlinear case, you have a whole, when you have about 50 different versions of NLS. The easy ones are the ones that mathematicians deal with. So there is Schrödinger-Poisson, which is the convolution of 1 over x. So in 3D, convolution is the Poisson equation. This is called the Hartree equation. If the interaction is a delta, you get the Gross-Pitayevsky, which is a cubic. So if you have here just a psi square, modulus of psi square that multiplies psi, that's cubic. So you have these equations mathematicians like and do a lot of work on blow up and so. But then the real physics starts with increasing complex coupled system. You have the Hartree-Fock system, Kohn-Shahn system, time-dependent density function, and multiplication Hartree-Fock boson. So these are nonlinear Schrödinger equations, and you want to derive that from the linear equation, from the linear Schrödinger equation. So what do physicists do? They make an ansatz for the many-body wave function. So you have a psi n. that lives in n variables. So, I mean, if you go beyond, let's say, helium with 2 electrons, I mean, you have the curse of dimensionality. If you want to do that for carbon, 12 electrons, you have 3 R3 10, so you exponentially grow the complexity. You cannot even write down any solution on any supercomputer. So that's mathematically easy. You get global solutions by Cato and something for the linear Schrödinger equation, but you can never use it in practice. So what you do is you make an ansatz, you make a product ansatz, so a product of the same wave function evaluated at all the positions. That's a Hartree ansatz for condensates. You make it, so you make ansatz 1. So the same wave function, that's a condensate. Bose-Einstein. So that's for bosons, where the wave function has to be symmetrized. Now if you have fermions, so psi n is anti-symmetrized, this means if you interchange 2 positions, you change the sign. If 2 are the same, it's 0. That's the Pauli exclusion principle. 2 quantum particles cannot be in the same state. You need the spin for the electrons to have 2 in the same orbital. So what do? You take a determinant. I spare the details. You take n wave function, the orbitals, you evaluate them at the n positions, and then you create a matrix, and you take the determinant of that matrix. Okay? And then, so you take an initial state that is on the submanifold extremely restricted of 1 Slater determinant. If there is non-zero interaction, you fly out of this manifold immediately, so there's work to be done if you want to do this as a time-dependent thing. And then you take linear combinations. Which comes with several names, multi-configuration. Time-dependent Hartree fog. Okay, so from the functional analysis point of view, you want to approximate an antisymmetric wave function in n variables. So if you take only 1 Slater determinant, you have a very small subspace. If you take m of this Slater determinants and n goes to infinity, you can dream of spanning your space with antisymmetrized Slater determinants. So that's multi-configuration theory, which is something that quantum chemists and quantum especially use a lot. So these are ways to get rid of these n dimensions. Then physicists, so I learned that in my many-body quantum physics course, so I'm also a trained physicist. I did both masters. You plug it in, you calculate, and then you have small terms, and you throw them away. And I will never forget, I asked the professor, how do you know it's small? You know, okay? So that's the way you do it, and you get very useful equations. So the mathematician, of course, will first ask, which object converges to which object, and how do you measure it converges? You have to introduce norm, and all our apparatus, which is essentially to do something that is clear. Then you put the 1 over n in front of the interaction on the many-body level. Then you reformulate the n-body Schrödinger equation as a hierarchy. This is the BBGKY hierarchy. Y here is the French part. It's Jacques Yvon. Claude will comment on that, I think. Then you pass the limit in hierarchy. And you identify the limit equation. And then comes the hard part. Either you can prove uniqueness of the limit, or you prove the factorization, which is, if it's a product, and the phi square is a probability distribution, that's something like molecular chaos, independent particles. So that's the quantum version of the molecular chaos assumption we heard several times. Okay, so that's the program. And this program, we worked out, the 3 of us, François, Claude, and myself. This is a bottle of Markovitch wine. So this is the only thing where Peter Markovitch is in the picture here. So this again, this is in Chateau Truden. So the 3 of us worked that out in 2000, the weak coupling limit of the n-particle Schrödinger equation. And for bounded potential, it's relatively easy. So we could do the limit, but we could not prove the uniqueness of the limit. And then there's a long story. I make it very short. There was a meeting in Lumini at the CIRM where Hongzhe was there and where Francois came up with the idea of modifying the trace norm with kinetic energy. So it's a compressed trace norm. And in the end, again, Laszlo and Hongzhe, they did it, telling us that they do not work on it. So then there was Claude, for the first time, he was really a bit upset. And then we made it clear. First paper was a note class, and then they had the CPM paper where they published the full result, which again, technically is extremely hard. To work with these compressed trace norms is extremely hard. So this is a very important paper that there's an old paper of Herbert Spohn, a review of modern physics, where he somewhat in intuitively way gives the program. It's not rigorous, there is even some mistakes, but don't care. It's a very, very good and valuable paper to read, okay? So we could put that on a very solid mathematical setting, and then many people applied it for very hard technical problems. Second series of papers with Claude is the time-dependent Hartree-Fock. So you take one Slater determinant as initial data, and then you have to control that. So we were working on that together with Alex Gottlieb. So that's, again, in Chateau Truden with my daughter Inma at the time. So it's also a funny story because, you know, Claude was raising Magali, his daughter, to a large extent as a single father. And then when I came with Inma from Brussels, when we stayed in Paris at Claude's place, so it was a similar situation in the next generation. And Alex is an interesting guy. He's a student of Alex Jorin. He did his PhD in Berkeley. Extremely strong and honest guy, but not able to make a career in science. So I kept him for 10 years in Vienna, but he always shoot in his leg. Sometimes you have very, very valuable scientists who do not make it in the system. That's something. So around Claude, we saved some of these scientists. Okay, and then we did a series of papers on tandem and Hartree-Fock, and also with Bernard Ducommet on if you have an M-parting interaction. So that was the second line of papers. And then for this multi-configuration tandem and Hartree-Fock, so when you take linear combinations of later determinants that many physicists and quantum mechanics use, and the convergence when M goes, if you take infinitely many linear combinations, it converges toward the true solution. That's a legend. Christian Lubich once insulted these people saying there is no proof, it's not clear if even numerically if this does. But it's a very important method, but there was nothing mathematically. So we joined forces with Isabelle Cateau and Sabert Trabelsi. He was a PhD student, and Isabelle, Claude, and myself, we supervised together. That's Christophe Pollard, a PhD student of François, and that's Maria. So Maria is here, and I have to say there's one mistake on the poster. The prize Claude received from the hands of Felipe, the sixth, it was not the Sion Prize, it was the ECM Prize, and Maria was the president of ECM at that time. So to clarify this, I made one mistake, but Maria is here, and we get it. So that's a nice photo in Rue d'Ulm with Sabert and Maria. So we setting analysis, so we really explain what these equations are, the fiber bundles and everything, so in a clear mathematical language. Unfortunately, that was 2010. That was the moment where I essentially stopped doing this kind of theorems only on the side, because then I talked to experimental physicists. So we were very proud of this paper. I mean, this was really, really good paper in the Archive of Rational Mechanics. The interest of the experimental physicists, so Pauli Institute was really deploying its scientific potential. So I was talking a lot with informatics people and experimental physicists. They would not even listen if you start to explain one of these papers. But they would say, I have this problem, I need a 3D simulation. Can you do a model where temperature comes in? I solve Schrödinger equation with white noise. Can you do that? Long-time simulation. We open the trap, free flight, picture. So the experimental physicist would come with completely different questions. They would say, this kind of results has zero interest. The final point of that was I gave a talk at ENS Saclay on the invitation of Alain Aspect, how mathematicians can be useful for physicists. And then we had long discussions with Alain Aspect, so François was there, some mathematicians. In the modeling, yes, the physicists, the quantum mathematicians who explain them how this neural network, this machine learning really works. Can you control the error? What is really done there? But they will not be interested if you give them a rigorous proof, epsilon goes to 0 in some crazy piece of space. Okay, so from that moment on, I changed my work. So I do on the side rigorous mathematics with proofs, but that's not the main issue if you work with physicists. So to finish, if I should describe Claude, and this was a word that several people in the last days were using, generosity. And Claude, so we had some not so nice experience. So the life of Claude is not always a bed of roses, and not everybody is nice to Claude. He also has enemies, and people take advantage of him, okay, scientifically. So he spreads around his ideas, and that's what he was teaching me. You tell people, I have this idea, even for the risk that they take the idea and publish without you, and this was the key to do the idea. He told me, don't become somewhat closed. And so that's one of the philosophy of Claude. Be generous. It's a big luxury to be generous in money and everything. So Claude helps people. Some of them exploit him, take advantage. He said, you don't care. You only focus on the positive people. And in the end, the love you make is equal to the love you take. In the end, you gain a lot. So this is a big message from Claude. If somebody takes your idea, uses it, don't make a war, just stay friends with the people and continue. That's life. People are like this. But stay generous, and that's what I learned from Claude and the people around him. So most people in this room are of that kind. So of course, there's some correlation. If you're a friend of Claude, you're not one of these people. So that's a big thank you to Claude that he was teaching me this lesson. And I want to finish with a picture. Christo was in Paris and wrapping the Arc de Triomphe, and I took Claude and Yvette at that time. And there's this really nice picture of Claude with Yvette under the wrapped Arc de Triomphe. Thank you.